So today we continue the discussion and the construction of non-abelian gauge series, and I'm going to start to discuss the problem of gauge fixing and how gauge fixing affects the quantization method in path integral. So non-abelian gauge theory. And I just discussed very briefly at the end of last lecture that a pure gauge theory can be coupled to matter fields by just replacing ordinary derivative by covariant derivative, which is, of course, a bit short. So we are going to discuss the coupling of gauge theories with matter later on, I think in the last lecture. But at the moment, I just consider a pure non-abelian gauge theory, so there are only the gauge degrees of freedom, only vector spin 1 bosons, because as you have seen, the dynamics of a non-abelian gauge field is already something complicated with non-trivial dynamics and non-trivial equation of motion. So I'm going to first do some reminders of what we did yesterday. Then I'm going to discuss the issue of how you perform the gauge fixing, which is essentially the same issue that in Maxwell and QED theory. From the point of view of the principle of why one should do gauge fixing, but we are going to see that when trying to perform a path integral quantization. The effect of and the treatment to perform gauge fixing is more subtle. It's more complicated, but also much more interesting than in the U1 Maxwell theory, because it involves what's called the Faddeev-Popov determinant. Popov determinant. Okay. So, first reminders. So, remember, well, I will mostly consider a case of a pure SU2, but that's generalization. Huh? And SU2 is defined by the generator of the Lie algebra. So, the generators of the Lie algebra are TA, which was 1/2 of sigma A, where sigma A has the Pauli matrices. Of course, the Lie algebra is just the algebra of traceless Hermitian matrices. You can choose the basis provided by Pauli matrices, so it's dimension 3. Okay, and we have seen that in order to define a gauge theory, we need gauge fields. So vector potential, A mu. But now they are labeled by A, going from 1 to 3. And so this is a real field, the component of a real field. The algebra Lorentz. And they can be recast into a field that I'm going to note A mu, which is just A mu A, T A, which is a 2x2 matrix with 3 independent elements give us the 3 gauge field associated to the 3 charges of the series. Yeah. 3 gauge field. Since 3 charges, because we have 3 generators. Okay, and we have seen that out of that, the analog of Maxwell potential for the electromagnetic field, we can define the field strength F mu nu, which is just defined as in Maxwell's theory as the commutator of covariant derivative. So it's I times d mu d nu, and therefore it's d mu a nu minus d nu a mu minus I, the commutator of the matrix A mu with the matrix A nu. Remember, A mu is a 2 by 2 matrix. And the covariant derivative acting on a field in the adjoint representation. So since A mu is a field in the element of the Lie algebra defines the adjoint representation of G. So A mu belongs to the adjoint representation. And d mu is defined as well, let's see. Let's write a gauge transformation just a modification by, if we change by an element alpha of x of the Lie algebra. So it's going to be alpha a of x Ta. So it's a field with 3 components, but it's a scalar field here. And the gauge transformation of A mu means that we transform A mu of x into A mu of x plus the covariant derivative of alpha of x with d mu, the covariant derivative of alpha of x is the ordinary derivative of alpha minus I times the commutator of A mu of x with alpha of x. Okay, and that's a general definition of covariant derivative. Acting on alpha, any fields belonging to the adjoint representation. We have seen that it's different. The covariant derivative is defined differently for fields in the fundamental representation, like the matter fields that have been considered, but that's all what we need here at that level. Okay. And we have seen that the action, the action of the classical field is just taken to be the action associated to a field configuration A. It's just basically the integral of a space-time of trace of F mu nu. Remember, F is a 2 by 2 matrix. So this is a trace over 2 by 2. So this trace refers to the indices of the group. And in addition, you sum over the Lorentz indices. And there was just a coupling constant, which I think was minus 1 over 2 G squared. Okay. And G was the coupling constant. Okay. So now why do we do gauge fixing? Well, we need to perform gauge fixing, to gauge fix, to study the series, simply because different gauge field configuration differing by gauge transformation are physically equivalent. F mu nu, they get the same F mu nu up to local gauge transformation. And the action is invariant under F mu nu. So the physics is physics on performing gauge transformation. It's exactly like for the Maxwell theory. And in fact, it's because the theory has this symmetry under this global group SU2. It's convenient to re-express the physics in terms of a vector potential, because that's a good way to encode the physical degrees of freedom. But there is a lot of gauge transformation. Simply means that we have a huge, big redundancy through using a vector potential instead of electric and instead of E and B, electric and magnetic fields. Yes?
Can you remind me how F mu nu transforms under gauge transformation?
Under,
it can be derived.
Yeah, under a gauge transformation, F mu nu, so A mu transforms non-trivially, but F mu nu transforms covariantly. So F mu nu, so it means that it involves a derivative. This term means that it's not covariant. But F mu nu transforms as F mu nu minus I F mu nu alpha, which means that it transforms locally under a gauge transformation. There is no d mu. Okay?
There's no derivative.
Well, no derivative. So it's a local transformation. Okay. Remember, this means that, remember, alpha just label an infinitesimal Gauss transformation. So to define that, if you define G of x to be the identity matrix plus I alpha of x plus some higher order, so this is an element of the group, but this means that F mu nu transforms as G of x, F mu nu of x, F mu nu of x times G minus 1 of x. So you see, it doesn't depend on the value of F mu nu at other points, or the value of the gauge transformation at other points. It's really a local gauge transformation. But A doesn't transform like that, because there is a d mu alpha, which means that there is a d mu g. So the way the gauge potential transform depends on the derivative of the gauge transformation itself. So it's not local. Okay.
Are you calling it derivative non-local?
Pardon?
Are you calling it derivative non-local?
Yes, because it depends on what's happening in the neighboring. Okay, let's call it non-ultra-local. I think the mathematical definition is not ultra-local.
I mean, we're still talking about locality and stuff.
Yeah, yeah, okay, no, okay.
That you can just write.
Yeah, okay, so if you, okay. Okay, so prefer,
notion of
so it's a non-ultra local transformation. Yeah, if by local you mean something that depends only on the value of the transformation and a finite number of derivatives, that's okay. Then we call ultra-local if it depends only on what's happening at a given point and not at any infinitesimally close points. Okay? That's just an issue of terminology. Okay, so the physics doesn't depend on gauge transformation. there is a big redundancy, so there is, in fact, you can write the equation of motion and solve them, but many different gauge fields will be equivalent and solution of the same equation of motion. And in particular, if you try to just take this action and expand it in powers of G, there is a quadratic term in the action. The action, a term involving just 2 a mu, which is a standard, term of Maxwell theory, because it's just minus 1/4. Where is it written here? Just have to rewrite it with the correct factor. It's simply minus 1/4 of d mu a nu minus d nu a mu times d mu a nu minus d nu a mu. And the difference with the Maxwell theory is just that you have to add the color indices, the 3 colors, A equal 1, 2, 3, with sum over it. So you have 3 copies of 3 different gauge fields, but the linear term is exactly like in Maxwell. Okay, so it means that if you take the Fourier transform, so if you are in a momentum space by Fourier transform, you write that I'm now considering the Fourier transform as a function of some 4 momentum k. Okay, then this term, becomes in Fourier space just a quadratic, so it becomes, if I'm not mistaken, 1/2 of a mu of k d mu nu of k and a mu of k or minus k. Okay, so this means that there is a diagonal quadratic form, which is the same thing than in Maxwell. Well, there is a, but that's not important. And d mu nu of k is just minus k squared times h mu nu, the Minkowski tensor for space-time, plus, well, let's write mu nu here. Of course, it's plus k mu k nu. That's very standard. Okay, and you see that this this quadratic form has 0 modes. It has 0 eigenvalues. So this is a 4×4 matrix for each k. 4×4 matrix if the dimension of space is 4. Okay? So it has 4 eigenvalues, but one of its eigenvalues is a 0 mode is 0, simply because if you assume that you take an a mu of k, which is k mu times some function something, al, and it can be any function of the 4 momenta. Okay, then you can check easily that d mu nu a nu longitude. So basically that this, if you want, k mu d mu nu. Well, I'm lowering and raising indices because this is just a Minkowski metric. Minkowski metric, or the Euclidean matrix, because you can work also in Euclidean space. This is obviously 0, because this is minus k squared times k plus k squared times k. So this is zero mode. Okay. So of course, these zero modes correspond to the longitudinal modes of the electromagnetic field, because that corresponds to the mode where the polarization of a plane wave is in the same direction that the momentum of the wave. So it's just the standard longitudinal modes of the electromagnetic field, which are known to not physical. Okay.
What's
Yes.
the index next to A mu equals K mu?
Yeah, if I take that A mu of K is K mu times some number.
It's A
Okay.
rho.
Pardon? Well, no, it's AL. So, well, it can be some function of K.
Okay.
Okay, take a function of K, any function of K. Okay? But this is a scalar, and this is a vector. Then this is zero. And of course, an A mu which has these forms, if you go back to Fourier space, it means simply, well, that A mu is a derivative of a function of x. So, longitudinal modes correspond to A mu of x. This was hat equal d mu on some A of x. So it's a pure gauge. So that's why it's in physical. It's a field which is just given by a gauge transformation acting on the zero configuration of the configuration where A equals zero. So it's equivalent to, A mu equals zero by gauge transformation. Okay, so no surprise that the term is zero. Okay, okay, and then as for QED, as for Maxwell, if you want to naively quantize this theory, keeping just the quadratic term, neglecting the interaction, okay, either by canonical quantization or by path integral quantization, you are going to have a propagator, which now depends on mu and nu. Mu nu, which is the propagator. Which is going to be the inverse of this quadratic form, D. But this, since D has zero mode, this is not well defined. If we proceed naively, not well defined. So, as for QED, or for Maxwell, we need to fix a gauge. Gauge fixing is required as a technical. Yes?
Doesn't the mu has a color index?
That you are?
A color index?
Oh yes, there is everywhere there is a color index, but you see, d mu nu here is diagonal in A.
Okay, like the delta.
Yeah, because the linear term you have AA, so this is diagonal. Yeah. But that's a good point, yes. T is diagonal. So you have A going from 1 to 3, but for each A, d mu nu is the same. So you can write that you have a d mu nu AB, but it's just delta AB times mu. Okay.
And could you repeat why is that gauge fixing is required?
It requires if we want to quantize. It's convenient if you do classical theory.
Yeah.
Because
But how is
and-
this related to the fact that the G mu, the propagator is not well defined by longitudinal modes.
I'm going to show that.
Ah, okay.
Okay. So gauge fixing is required both classically, because then it's convenient to do the calculation of classical electrodynamics in a fixed gauge. But for quantization, it's required, because you want to get rid of this unphysical mode. I think that's something you did in some way and another way in QFT1. Okay. And of course, as for QED, we may use the various gauge fixing. And I'm going to use mostly, I'm going to use in this course a standard, so it's called the Lorentz Landau gauge. So, in fact, it corresponds to the standard Lorentz gauge in Maxwell theory, but it was one of the first to use it was Landau for QED for quantum theory. So that's why it's named Landau, I think. So simply, the gauge condition is that for each A mu A of X, we enforce that the ordinary derivative is 0. Okay. So you see, you have three conditions because you have A goes from 1 to 3. So in fact, this corresponds to 3 gauge conditions, one for each component of A mu. Okay, and this is enforced to be valid. So it's a derivative with respect to X for all values of X. So that's the standard Landau gauge. Okay? Which has the same advantage, in particular, of being a relativistic Lorentz and Poincaré invariant. So it's okay. And so, of course, this is for each A, but you can write it in, if you use the big A, simply as d mu of A mu equals 0 if you consider that A mu is just 2 by 2 matrix. Okay? Okay. So just that's the same equation, component by component, and working just in the adjoint representation. Okay. And then I'm going to use later a variant of this gauge, which is called the Feynman gauge, which is just a variant of this, where instead of enforcing that this is 0, you enforce that d mu of A mu is some fixed function. So epsilon of X is a fixed function. With this notation, it's a fixed 2 by 2 matrix. So it's a fixed function of X, of the position. So you choose a function in position space, which is in fact a 2 by 2 traceless Hermitian matrix. So you have given 3 functions. Okay, and you enforce this. Okay. Good. But there are many, many, many other gauge fixing procedures for non-abelian gauge theory. For instance, well, for some calculations, the axial gauge is more convenient. And for some other calculations, a light cone gauge is more convenient. So there are many others. Okay. Okay. So now I'm going to give a very general geometrical picture of what is a gauge fixing, which is going to be useful. In fact, it's a geometric picture that is valid both for Maxwell and for U1, but simply for Maxwell theory, a gauge fixing procedure is much more simple. Okay, so let me consider just the space. Where is it written? Okay. So I'm going to consider a big space, which is a space of all gauge field configuration. It's an infinite dimensional space. So let me write it here like this. So I consider a big space. Of course, it's going to be an infinite space, which I'm going to call A, which is a space of gauge fields, or potentials, A mu. So a point in the space, in this space, is just a function. It's the data of O A mu of x for all points of space. So it's a function. And in addition, it's a function with indices, so it's a 2x2 traceless Hermitian matrix. So it's a gauge field configuration. Okay? Okay. And in this space, of course, so we have A, and then we have a big group G, which is the group of local gauge transformations. Okay? So a point, an element of the group, I'm going to denote it G, a point in this very big group is just the data of a gauge, a local gauge transformation at each point. So it's an element of data of GE of x belonging to SU2, or my gauge group, for all x belonging to Minkowski space. And here that's the same. So it's a function from Minkowski space into SU2. So it's the space of all functions, well, with some regularity condition, from Minkowski space to SU2. Okay? Okay. And this group, G, acts on A. On capital A. Simply because to each point on the group, we associate the gauge transform. Transformation, the gauge transformed configuration that I'm going to call AG, which is just given by this for an infinitesimal gauge transformation, but what I call here. So A mu of G is just, with this notation, as we have seen, this is just G A G minus 1, and then there is the term corresponding to where is it written? I wrote it. Yes, plus I G D of G minus 1. Okay. So here you have a mu. If you think about the indices, this is a correct definition. Okay. Okay. So G acts on A. So this means that if if you have a gauge configuration A here, any gauge transformation maps it into another A. You see? So I'm just drawing in the blackboard, but so I'm in two-dimensional space, but you must think of this as infinite dimensional space of function. So you have here an orbit of the group. Here you have an orbit of G. This is the space of all gauge field configuration, gauge potentials that are equivalent by gauge transformation. Okay. Okay. And therefore, your rule configuration space is a foliation of the whole space by gauge orbits. Yes?
You say that one line is a bunch of theories which are equivalent under gauge transformations.
It's not a bunch of theories, it's a bunch of gauge potential of A mu, which are equivalent by any. Okay.
They are equivalent, like you can jump from one to the other by applying G to some
G. So if you are here,
can you jump from anywhere to anywhere by applying it?
No. You can, by gauge transformation, you can just jump from on this orbit. Okay. So two gauge configuration A and A prime belongs to the same orbit if there exists, if there is a G belonging to capital G such that A prime is A of G, or reciprocally if A is A prime of G minus 1.
So the only thing you need to check is whether like A mu and A mu, like whether A of X and A prime of X.
Yes. Well, you have to look whether you find a G. You have to find whether you can find a gauge transformation that maps G and G prime. So an orbit of G is a space of all A's equivalent by gauge transformation. It's a very general definition of if you have in math, if you have a space, X, and then a group G, which acts on X, then you define the orbits. I don't remember exactly I think the definition is G goes to X or something like that. There is a well-defined mathematical notation. G acts on X, well, of course in a transitive way, etc. And then you can define the quotient space of X by G, the space of orbits. Okay?
I was just wondering, it looks like there should be a more insightful way of stating that if your group is specifically SU2. Isn't it just like so you're asking whether if you take two matrices, whether you can jump from one to the other by applying the same member of SU2 to the left and to the right?
Yeah.
Or like G and G minus 1.
Yeah. No, but you see, the solution will involve some differential equation because there is a derivative. Well, they may be for SU2, but what I'm going to state here is general. It's for any group.
So you have conditions G.
G is an element of the group.
If,
Here,
what you write there is that it's any function from Minkowski space to SU2.
Yes.
Then taking a partial derivative is not even a sensible thing.
No, let's take any function which is smooth in the sense that it has derivative. Okay? Smooth function. In a sense that I'm not. course. You need the derivative. So you assume that this is a function which has a derivative. Okay? So there is a way to define that in space of well-defined functions, some kind of Sobolev space, but I'm not going to discuss it. Yes?
So even though we have an infinite dimensional
Yes.
space because we are treating functions,
Yes.
is there any information left about the fact that we have the three colors for our gauge fields?
Well, the colors are everywhere. Simply here I have used very compact notation where by A I denote an A mu of x, but of course it depends on A. So in fact, the coordinates are labeled by x, mu, and A. Okay. Of course. So, but simply I'm using this geometrical picture because it's all what's important. Okay, so you have this picture. And of course, all gauge configuration in an orbit are equivalent gauge transformations, so they must describe the same physical configuration of the field. Exactly like in quantum, in Maxwell's theory, where the group is U1, the value of the electric and the magnetic field is the same for each gauge potential configuration along an orbit. It's a bit more complicated for gauge theory because it's a non-abelian field, so there is still an action of the local gauge transformation, but up to the symmetry, they are equivalent at the same electric and magnetic field configuration. Okay? So, physical configuration, if you want, with this picture, physical configuration equal orbits, given orbit. Okay? So, we can define a space of, do I have a notation here for this? So I can define the space of physically configuration C. I'm sorry, this is not C. This is a curly C. Just by the space of gauge potential divided or quotiented, this is a math definition, by the action of the group G. Okay, and so this is a space of orbits. Okay. So this is a space of physically inequivalent configuration of the field. Inequivalent configurations. Classical configuration. Okay? So in Maxwell's theory, it will be the space of inequivalent configuration of electric and magnetic fields. Not necessarily solution of Maxwell equation, but so it's a space in which we must solve the Maxwell equation, for instance. Or okay. Okay, so now if we have this picture, what corresponds to gauge fixing? This corresponds to pick a representative A inside each orbit. So gauge fixing means that these orbits will be represented by some field configuration A, satisfying a gauge condition. In the different orbits, we'll pick a gauge configuration corresponding to a satisfying. Okay. So gauge fixing corresponds to define what's called the gauge slice. Which is transverse to the orbits. Transverse to the orbits. That picks one A in each orbit. So mathematically, a bit more mathematical language, this means that define a gauge slice transverse to the orbits, or the action of orbits, by a gauge fixing condition. So for instance, this red slice is a set of all A mu that satisfies Lorentz gauge. Okay, and if we work properly, then we pick only one point in each orbit, and the configuration makes sense. Okay? So, gauge fixing corresponds just to finding a function such that the set of zeros of this function is transverse to the orbits.
Like there, you just say you pick a representative for every distance.
Yes.
Is there a reason why you draw it as a line there? Why it's kind of a smooth thing?
Yeah, well, it could. Yeah, no, of course, you could take something very irregular, but it's better to take something regular. And if you take a gauge fixing condition like the Feynman gauge or the Lorentz gauge, which is in substance a smooth function of A and its derivative, then its zeros are going to define a smooth slide. Okay, you see. So if the gauge fixing condition is smooth in some sense, is regular, then the slice is regular in the sense that I'm not going to define at all. Okay. You see. So gauge fixing means that we choose gauge fixing means that we choose a function, a gauge fixing function that I'm going to call f of A. Which is a function from the space of all A mu into the Lie algebra of the group. G, which in our case is SU2. It's a function in the Lie algebra, but because we have seen that for instance, the Lorentz gauge, we need 3 gauge fixing conditions. So we need that d mu of A mu equals 0, where this is a 2 by 2 matrix. You see. So if you take a general A mu and you compute d mu of A mu, you get a 2 by 2 matrix, which is a traceless Hermitian 2 by 2 matrix, which is in general non-zero. And the gauge fixing condition means that I keep only the A such that this is 0. You see. So for instance, example, Lorentz gauge. The function A is just that the function A is just defined by d mu A mu. So f of A, this is a function. This is when applied to given x is d mu A mu of x, which is a 2x2 matrix. So it's d mu A of x times TA, which is it's a traceless 2x2 matrix, Hermitian. And the condition is that this function is 0. And this picks a transformation. Okay? Okay? But more precisely, since this vanishes, so it's a condition for any points. In fact, it's not a function in the algebra of the gauge group, but it's a Lie algebra into the function of the big group of local gauge transformation. But a group of local gauge transformation is just the products of G times G for each. It's an infinite product of the gauge group for each point of space-time. So if you like mathematical notation, you can do this G times Minkowski space. It means simply that it's an infinite abelian product of infinite products of groups associated to each point of space. Okay. And of course, this Lie algebra of the group G is just the products of the Lie algebra of SU2. Okay. If we want to be mathematically rigorous. But this means simply that you see, so this is FA for Lorentz gauge. Is that, and in general, we are going to find the function f of A, which is defined some function of A, d mu A, d mu A. You can construct gauge that depends on A and some of their derivatives. So for instance, you see a Lorentz gauge depends only on A, but if you find, for instance, an axial or a Coulomb gauge, it will depend only on the value of A, since the axial gauge is, the axial gauge is A0 in the time direction is 0. And the Coulomb gauge is, in fact, no, the Coulomb gauge is that the spatial divergence of A is equal to 0. So you see. So in general, f is a function of A and its derivative at a given point. Okay. But this is the example I'm going to do. Okay. And for the Feynman gauge, for Feynman gauge, FA of x is just d mu A mu minus epsilon of x. Okay. So it's this function. So this is Lorentz, and this is Feynman. And Feynman is just f Lorentz plus some function epsilon. Okay. Minus. Okay. So this is just an abstract and compact way to represent this choice. Okay. And so you see that different choice, different gauge fixing corresponds to different function f of a, and they give different slices. Okay. So for instance, this is a slice corresponding to the Lorentz gauge, but you may consider a Feynman gauge with epsilon different from 0, and then you are going to get a different gauge fixing. You see. Or you are going to get something like that. You see, so you could say that, for instance, this is Lorentz, this is Feynman, and this is another Feynman, or this is axial gauge, for instance. Okay, but all this choice of gauge fixing should be equivalent. Okay. Okay. So this is nothing deep. This is exactly the same for Maxwell theory. It is a geometrical picture which is convenient to keep in mind. Okay? Okay, so now the question is, how do I try to build a path integral, a functional integral? So I want to build, now I want to construct a functional integral over the space of inequivalent configurations. So in fact, quantization means I want to build a functional integral over C, the space of orbits. Okay? And this is complicated, so standard recipe is rather build a functional integral over a slice, because we know that each point in a given slice corresponds to a different physical inequivalent, but in a gauge invariant way. Why? So that independent of the gauge fixing condition. So we want to integrate over this space, for instance, but taking into account the fact that, for instance, on these slides and on these slides, we must associate the same weight to this element and to this element. You see, to this element and this element in the space, because they correspond to the same element in the space of orbits. So the integration measure should depend on n. The integration measure should depend on the gauge fixing condition f of a. Okay? And you see, geometrically, you see immediately why. Okay. Okay, so now here is a recipe that has so here is a recipe how to build a functional integral. And this is something that has been devised by Fadeev and Popov. Of course, I never remember how many. Faddeev has 1D and 2V. Ludwig Faddeev is one of the greatest mathematical physicists. He's from Moscow, but he's still alive. So if you met him, you'll be. But also, some of these ideas were independently devised by Bryce DeWitt, US physicist who was one of the pioneers in quantum gravity and gauge theories, and by Feynman also, of course. Okay, but the name. Okay, so we are going to start from an abstract configuration, which is that we start from the functional integral, which is which makes sense, which is integral over all gauge field configuration, dA of exponential of minus S Young-Mills over A. Okay? So I'm going to be working in Euclidean formalism just to get rid of the I factors, but that's technical. Everything I'm doing here can be done in a functional integral at real time. S Young-Mills is still defined by the action there. It's just a minus 1 over 2g trace of f squared. And dA is formally just, as usual, products over all points of space-time of dA of x, which means products over all points in space-time, products of mu, and products of A of dA mu A of x. Okay? So you sum over all points in space-time, you sum over all components of A mu, and you sum over all the generators. So this is an of A. So A goes from 1 to 3, remember? Mu goes from 1 to 4 if I am in 4-dimensional space-time, and this is a formal infinite sum over all points in Minkowski space or in Euclidean space. Okay? Okay, so this is a very big integral, functional integral, and this integral a priori makes sense because we are integrating over all A, you see? And so the problem is not that this integral is ill-defined. The problem is that the action is the same. The weight exponential of minus action is the same on is constant under orbits. Okay, so this integral is finite. Well, up to the point that this integral makes sense. So it's an integral over A, the space of all gauge field configuration. Okay?
Even though
yes? What?
So there's certain, like, you're counting every point on one orbit.
Yes.
But they're all equivalent. You can only count them once.
No, you can count them several times. They are equivalent.
You're not fixing a gauge.
At the moment,
you're counting the same points, the same theory with the same gauge.
No, you can. And
you're counting the same physics multiple times because you have some redundant freedom that you have.
Yes, yes. But the redundancy is just labeled by the gauge group. And the gauge group is many copies of SU2. So I can integrate over SU2. It has a finite volume. I'm overcounting.
What's the volume of the group?
The volume of a Lie group, you know, a Lie group, G, like SU2. A Lie group like G equal SU2 has an invariant measure over G called the R measure. Okay? Which is defined uniquely, well, up to left and right, but for reducible group, well, for basically simple enough group, it's the same. So it's a measure, let's say, d mu over G, which is such that when you make a global gets, you multiply by the group, it's invariant under the action of the group. So you can define just the integral over the group of d mu G, and this gives you the volume of the gauge group G.
We're talking about two different integrals here, I think.
Pardon?
You're saying there that you integrate over A being the entire
No.
circle.
Yeah. No, I'm integrate over A, but I mean that all the different points in a different orbit are, this is an orbit of the group G.
Yes.
So basically, if you take the volume of a small element here, and then you multiply by the action of the group, you get the volume of the volume of the orbit.
You multiply a volume by an action of a group?
Oh, okay. My language is not very good. I take a little element and then I let the group act. And in that, I can cover the whole orbit. And out of the volume of a small element, let's say a small element here, I can get the volume of everything here by just letting the group acting on that. Okay? And these are the finite volume. Okay. Okay, you'll see, because the trick of gauge fixing of Paddeev and Popov does the job. So you are going to see how one does that. Okay. So the point is that this path integral, which is a big integral over A, makes sense. No gauge fixing yet. And the important point is that this integral is invariant under the action of the group, because we are integrating over the whole space. So in particular, this measure is invariant under gauge transformation. This means that if you compare the volume element of a gauge field configuration and the volume element of a gauge transform gauge field configuration, it's the same. It's a property. It's an important property of this measure. It is invariant under gauge transformation. So in other words, d of A is equal to equivalent to d of AG, whatever G belonging to the big group is. So the action is invariant, and the measure is invariant. So this object is gauge invariant. Okay? Okay? Okay. So now we want to write this equation as an equation over a slice, of a gauge slice. Can we write this big integral? Let's call it Z. Okay, so this is Z. Can we write Z? So this is an integral over A. Okay, can we write this? Can we rewrite Z as an integral over a slice of something? So factor out the action of the group. Okay? Okay. So in order to do that, there is a beautiful trick. I'm going to call trick one, because there is a second trick that I won't have time to discuss. I'll discuss it tomorrow. The first trick is something a bit stupid. Let's call how to write 1, the number 1, as an integral. Okay? So, I'm going first to discuss this in the case where I'm integrating over just a number. Well, we can call it A, but okay, so I want to define what is the integral over a number A that goes to minus infinity to plus infinity of delta of A minus A naught. In my note, it's called X, but well, let's call it A because A is a gauge fixing. Okay, so obviously this is 1. Okay, I hope you agree with that. Okay, now let's assume that A naught is just defined in the following way. We have A, we have some function f of A, and let's assume that it's a function that has only 1, 0. F of A equals 0 has only one solution, which is A0. So f of A0 equals 0. So this is a function f, this is A0. Okay? So then it's easy to see that we can rewrite this as an integral from minus infinity to plus infinity of dA delta of f of A times the absolute value of the derivative of A. Okay? You just make a change of variable to change A. You write that f of A is approximately f prime of A naught times A minus A naught in the vicinity of A naught, and you use the fact that the delta function of A minus, that basically the delta function of any function x times some number, c, is c minus 1 times delta of x. Okay. So you are just making a change of variable. Okay? And of course, f prime of A appears in the integral only when A equals A0, so it's f prime of A0. Okay, so this is the basic integral we need. We need this trivial result. 1 equal integral over A of f prime of A times delta of f of A. Okay, if f of A has only 1, 0. Okay? Okay. So now let's do the same trick. Now, what's happening if A is a n-dimensional vector, and we try to do the same trick in Rn. So now I want to write that I want to integrate dA over A minus A naught. So I want to write 1 equal integral dN A delta of A minus A0. Okay, and I'm going to assume now that A0 is a point, so it's a point in Rn. So it has to be satisfied by n condition. So I'm going to choose a function f, a vector field f of A, which is f1, fn. So that's A0 is defined by such that f of A equals 0, and 0 is a vector, has only one solution, which is A0. Okay, so now we are in Rn, and there is a point A0, which is defined by the n condition that f1 of A equals 0 up to fn equals 0. Okay? So now the question is, can we write this as an integral over dA times a delta function of f of A? And delta function of f of A means simply that this is a product from I equal 1 to n of the ordinary delta function of fi of A1, An. Okay, so it's a product of n delta function, but I write this as delta of f of A. Okay? Well, the factor in front of this is just the absolute value of the determinant of the Jacobian dfi divided by dag. So the coefficient here is just the determinant of the Jacobian of the, if you want to change the variables, A to F. Okay? This is the absolute value of determinant of dfi over dag at the point A. Okay. And that's an easy determinant. Okay? And I'm going to write this as simply the matrix F prime. So let me write this simply as the determinant, well, the determinant of F prime of A. So this is the absolute value of the determinant of A. So remember that with this notation, A is a vector, F is a vector function, it's a vector field, and therefore F prime of A is a matrix, Jacobian matrix. Okay? This is notation, shortened notation for this. Okay? Okay. So now, let's do the same trick for this. I start from my integral, big integral here. So this was for functions. Now for integral over A, over my big configuration. Okay. Okay, so I choose a gate fixing condition for function f of A. Okay? Defined as it is defined above. Okay? So it's a set of gate fixing conditions. Okay? And then I'm going to consider that for, okay, I'm going to write 1 as an integral over the gauge group G. Okay? So as I said, you know, when you have a gauge group, you have a R measure. Okay? So you can write something which is just that 1 is the integral over a group G of d mu of G times delta of G and G0, where this is the R measure, and this is Dirac delta function on the group. Okay. So now assume that G naught is defined by being the zero of a function f of G naught. So there is a function f of G0. Well, it's not exactly the same than, well, okay. Let's call this, well, let's use the same notation. But here this is a function, f is a function from the group into its Lie algebra. Okay. So we have f of G0 equals 0 means that we have n condition that the function of G0 are equal to 0, where n is the dimension of the group. Okay? Something like that. Okay? Okay. So this means that you can write f as f of G as, you can write that f of G is a collection of function, can be written as FA TA so it's a collection of the dimension of the group 3 for SU3. So it's a collection of A functions for SU3. Okay? So now, let me define the Jacobian of this function. Can I define the Jacobian of this function? The Jacobian matrix of this function f at a given point G. Okay. So Jacobians means I'm doing the derivative of the function f. Okay, so for that, this means that I make a small variation of G. So I change G into G times 1 plus I alpha, where alpha is an element of the Lie group. Alpha belongs to the Lie algebra. So it's, for SU2, it's a standard 2x2 traceless Hermitian matrix. Okay? And in order to define a Jacobian matrix, I compare FA of G with FA of G prime. So what I compute FA of G times 1 plus I alpha. Okay? And alpha, since it's an element of the Lie algebra, I can write it as alpha A times TA. So each alpha A is a number. And so this is a function of the alpha A. And I take the derivative of this function of the alpha by alpha B. And once I've taken the derivative, I take alpha equals 0. Is it clear? I'm sorry, this is maybe a bit... Okay. Okay. So by definition, you say this is a derivative of a function with respect to a number. So this is a matrix element. So let me write this as so this is a matrix element that I'm going to denote simply dB of FA. at G. Okay? So now this is a matrix element. This is a matrix element of a n by n matrix, where n is the dimension of the group. So for SU2 is 3. Okay? And so this matrix, I'm going to denote it simply F prime of G. So F prime of G is a shorthand notation for the matrix whose matrix elements are dB of Fa of G, where dB of Fa of G are d of Fa of G times 1 plus I alpha, the derivative with respect to the component B of alpha. Okay? So this is.
I mean, we should treat alpha as a function?
Yeah.
So
Well, no, here this is a number. I'm working on the group. I'm working on the group, for example, SU2. But now you can generalize that to the gauge group simply by taking this definition for at any x. So a copy of this.
So we'll take a function of the derivative.
Then we take a function. Yeah, we can take a functional derivative. But in this case, for the local gauge transformation, the functional derivative that will be just a delta function times x. Okay. Oh. Okay, so it's already time to stop. But so now let me just. Okay, so let me. I'm playing too much. So we need this. And now with this, let me just write one last formula, and we are going to continue next time. So let me here. Going up. Well, I can keep this front. Mid is going there. Okay, so this is 3, this was 4, this was 5. This was 6, and my 7th blackboard is going to be this one. Well, let me take this one. Okay. 7th blackboard is going to be this one. Okay. I'm going to apply this nice formula, these two nice formula, to ZA by realizing that, you see, for each A, in the integral, my big integral, my B integral Z, which is defined as the integral over all gauge field configuration, there is a G, hopefully unique, okay, such that my gauge fixing condition of AG is 0. I choose a A somewhere here. There is always a G so that I move A on the gauge slides. You see? Of course, this G depends on A. This G depends on A and on F, the choice of gauge fixing condition. So let me call it, let's note it, Gf of A. It's a function of A, and this function depends on the gauge fixing condition. Okay? And now, let's multiply Z, which is integral over dA times exponential of minus S Young mice of A, by 1. But for each A, I write 1 as exponential minus S Young-Mills of A. And for each A, I write 1 as integral of the gauge group, an element of the gauge group with a R measure, so let's call it d mu of G to be very precise, times delta of G minus G f of A. Okay? Okay, I have not changed anything. And tomorrow, I'm going to show that this can be rewritten by this trick as an integral over A, exponential of minus S Young-Mills, a delta function of f of A the absolute value of the determinant of some Jacobian times the integral of a gauge group G of d mu of G, which is the volume of the gauge group G that factorizes. It's a constant, independent of A. So I'm going to show tomorrow that thanks to gauge invariance, I can rewrite this condition, which is non-trivial G, as a delta function of the. So this is a delta function on A that enforces the gauge fixing. Okay, and this determinant of Jacobian that comes from this kind of trick that I'm going to show is the famous Faddeev-Popov determinant. Okay, but I have no time to do this today. But you'll see that also quite abstract. This is a straightforward application of what I explained at length a bit. So it was a bit formal, but this ended up with this formula. Okay, so see you tomorrow.